In this video today, we are going to see about subspaces, their definition, and a few sums under subspaces. So now comes the definition of a subspace. Any non-empty subset W of a vector space V over a field F, you call it as a subspace if by itself this W becomes a vector space. All operations of addition and scalar multiplication has to be satisfied by this W. Then you call that as a subspace of V. Okay, but if you take this zero space and V as by itself, V itself is a subspace for itself, and singleton 0 is also a subspace of V. We call these two as trivial subspaces. Okay, and then instead of proving all those 8 conditions which we check for a vector space, actually it is enough if we can prove these 2 conditions alone. Like suppose I consider 2 elements x and y vectors from W. When you add that scalar addition, vector addition, if you do x plus y, that should be in W. Also that scalar multiplication, one A from the field F, when I multiply with x, it should be in W. When these 2 conditions are satisfied, then you call the subset W to be a subspace. A subset becomes a subspace if it satisfies these 2 conditions. X plus y belongs to W, Ax also belongs to W. Now combining these 2 can be given as one single condition. We call it as the single condition criterion. A into x plus y is Ax plus Ay. Now we are going to just see a few problems under subspace. We are going to check whether a given set can it be a subspace of a vector space. Now in this sum we have to check whether W equal to A1, A2, A3, it's taken from R cube with a condition A1 equal to 3A2 and A3 equal to minus A2. We want to check whether W is a subspace of R cube. So 2 conditions we can check, or together it can be checked as a single condition criterion also. So the first one, we are taking U, V. 2 elements we are going to take from W, and we will prove that this U plus V, whenever I add these 2 elements, that will also be an element of W. Okay, so now my U is A1, A2, A3, satisfying the condition A1 equal to 3A2 and A3 equal to minus A2. V belongs to W. B1, B2, B3 will also satisfy the condition B1 equal to 3, B2 and B3 equal to minus B2. Now let us consider U plus V. By addition, how do we add? Component by component, they are added. The first component of U is added with the first component of V, the first component with the first component, second component with the second component, third with the third. That's how I get U plus V equal to A1 plus B1, A2 plus B2, A3 plus B3. Now this U plus V, if it should be an element of W, then it will satisfy this condition. So let's check what is that condition. The first one, A1 plus B1 is equal to 3 times the second component. What is the second component? A2 plus B2. So I have to get this as A1 plus B1 equal to 3 times the second component A2 plus B2. But what is my A1? My A1 is 3A2 and B1 is 3B2. Now taking out 3 common, it is A2 plus B2. The first condition, first component equal to 3 times second component is satisfied here, and then the third component equal to minus of the second component. What's my third component here? A3 plus B3. By definition, what is my A3? Minus A2 and B3 is minus B2. Now taking out that negative common, I am able to get A3 plus B3 equal to minus of A2 plus B2, which implies that U plus V belongs to W. Now coming to the next, scalar multiplication, multiply with alpha, all elements, all components, they get multiplied by alpha. Now again we will check whether this condition is getting satisfied. So the first one is alpha times A1 means it is alpha times what is A1. Take A1 from here, it is 3A2. That 3 can be written outside. So it is 3 times alpha A2. Similarly, alpha A3 equal to alpha into minus A2 or minus of alpha times A2. So both conditions are satisfied by alpha U. So alpha U also belongs to W. Once U plus V belongs to W, alpha times U belongs to W, then you call that W as a subspace of the given space R cube. Now next one, you want to check whether, again W, A1, A2, A3 with a different condition. 5 times A1 square minus 3 times A2 square, 6 times A3 square equal to 0 is a subspace of R cube. So again I will consider U, V and W. They will satisfy this condition. So 5A1 square minus 3A2 square, 6A3 square equal to 0. V is a member of W, so that also will satisfy the condition. Now let us consider U plus V. So adding them component by component, A1 plus B1, A2 plus B2, A3 plus B3. We want to check whether it can belong to W or not. It is not belonging to W because the condition is not getting satisfied. What is the condition? 5 times the square of the first component. 5 times square of the first component minus 3 times the square of the second component plus 6 times the square of the third component. If I expand this, I should be able to get it as 0. But if you expand this, you will see that it is not going to be 0. Therefore, we will conclude that W is not a subspace of R cube. The first condition U plus V belonging to W itself is not satisfied. So, we are not going to go for the second condition. So W is not a subspace of R cube. Next one, prove that set of all points on the x-axis in R cube is a subspace. X-axis, so by saying x-axis, a point on that means the components. How will you have the components? X component will be there, but whereas y and z component part will be 0. Okay, so this is how the elements will be A, 0, 0. Okay, so this is our W now. Now consider one U, consider one V in W. Let us check whether U plus V belongs to W. So add them. When you add A plus B, 0, 0 with 0, 0 plus 0. So that gives me my U plus V as A plus B, 0, comma 0. Now this belongs to W because both your Y and Z components, they are 0. So this U plus V is an element of W. Now multiply by alpha with U. So alpha A0 gives me alpha A0, 0. These two are again 0 and I have only alpha A. So this also belongs to W. Hence W becomes a subspace of R cube. Next one, we go to matrices. We are going to consider all M by N matrix and prove that W becomes a vector space where the transpose A transpose is equal to A. We are considering square matrices, N by N matrices. Okay, so it's given that A transpose equal to A. Whenever the transpose of one matrix is equal to the matrix, then you call it as a symmetric matrix. Okay, now consider two elements which are matrices from W. We know that all elements of W satisfies the transpose and the matrix are the same. So A and A transpose are the same, B and B transpose are the same. Now consider A plus B. What is A plus B? In the place of A, let me write A transpose. In the place of B, let me write B transpose. Now this can be written as A plus B whole transpose. So what do I get? The matrix is equal to the transpose of itself. So it is an element of W. A plus B is an element of W. Now scalar multiplication, take one alpha from R and A from W. A from W will satisfy A equal to A transpose. Now multiply this alpha with A. Now what is A? A is nothing but A transpose. Now I can write this alpha A transpose as alpha A the whole transpose because R is a R stands for real. real numbers only. So alpha A whole transpose. So this will imply that alpha A also belongs to W. Therefore W becomes a vector space.